At the beginning of this unit, we learned that the derivative of the natural log function is 1 over x, or the derivative of the natural log of some function, suppose we call that u, would be u prime over u, right? Now we want to look at integration involving the natural logarithm. So it would make sense that if the derivative of the natural log of x is 1 over x, that the integral of 1 over x would then have to be equal to the natural log of x. But there is a catch. Remember what the function, or the graph, I should say, of the natural log function looks like. If I were to graph the natural log function, you would get something that looks something like this right here, where it's crossing the x-axis at 1. That is to say, the natural log function has a natural domain restriction. We say that the domain is restricted at x here. X has to be greater than 0. That is to say, we cannot evaluate the natural log of a negative argument that is outside of the domain of the natural log function. So because the natural logarithm has a restricted domain, then we need to make sure that we take that into account when we are integrating its derivative, 1 over x. So what we effectively just need to make sure is that when we integrate 1 over x, that we get a natural logarithm such that we are evaluating the natural log of only positive values. Now ask yourself, do we have some type of tool that does that? And the answer is yes, absolute value. And what the absolute value does is it allows us to ensure that when we take the integral of 1 over x, which is simply the derivative of the natural log of x, when we integrate 1 over x, we are ensuring by putting the natural log, or by putting the absolute value around our argument of x, we're ensuring that we are taking care of our domain restriction, that we are only taking the natural log of positive arguments. So we would say that the integral of 1 over x dx is simply the natural log of the absolute value of x plus some value constant c. And in general, just in the same way that we said that the derivative of the natural log of u was equal to u prime over u, where u is just some function, we would say that the integral of u prime over u, if we go back the other way, that the integral of u prime over u has to be the natural log of the absolute value of u. And again, this is just to ensure that our natural logarithm takes into account that its natural domain restriction, where we're only taking the natural log of positive arguments, because the natural log function can only evaluate positive arguments. On this note, somewhat related, we would say that the derivative of the natural log of x, I'll write that this is just a brief note that we just want to make sure we know, that the derivative of the natural log of x is 1 over x. That the derivative of the natural log of the absolute value of x is also 1 over x. However, the integral of 1 over x can be the natural log of x only. All right, so when we take the derivative, or with the integral of both of these derivatives here, we can only get the natural log of the absolute value of x, I should say, plus c. Right? So really just making sure that when we're integrating, we want to make sure that we work in and build in that natural domain restriction of the natural log of x, where we're only considering the absolute value of our argument. Okay, so let's do an example of something like this. Let me clear this out of the way so we have some space to work with. Let's do a quick example. All right, so let's evaluate this integral here, and I'll just do this work right below. Let's evaluate this integral of x over x squared plus 1. Now, it might be helpful to make sure that we think of this integrand in terms of some function u. So I'm going to take my more complicated looking function, the denominator here, x squared plus 1. There's a lot more going on there. So if I said u is equal to x squared plus 1, that means u prime, or du, is equal to 2x dx. So if we think of this integrand in these terms of u, we could rewrite this as the integral, where our denominator is u, and our numerator here looks pretty close to being u prime, right? It looks pretty close to being 2x dx. We have an x. All we're missing is a 2. So we can multiply our integrand by 2 so long as we also multiply by 1/2. So we're not actually changing the value of this integrand. Now I can then, actually just keep it consistent. Now I can think of this as 1/2 integral 2x dx is simply u prime over u. So then this, if I integrate, we would say is equal to 1/2. Now, since it follows u prime over u, this would be the natural log of our argument u plus c. And let's plug in exactly what the absolute value of u is. This is 1/2 the natural log of, what did we say that was? X squared plus 1 plus c. So this would be our integral here. Okay, let me just kind of zoom out on that so you can see all that work together. Okay, all right, let's do just a few here before I talk about some other methods of integrating. Let's get that out of the way. Don't want to confuse anyone too much there. All right, so again, if we were to do something like number 1 here, this could easily be u prime over u, or the derivative of x over x itself. If I just move that 5 to the outside, well, that's pretty easy. Now I've just got 1x dx. So this is going to be equal to 5 times the natural log of the absolute value of x plus c. Okay. Some of these other ones are good problems for you to work with, so I won't do all of them here. But something like number 5, for example, would be another easy one, where what is the derivative of sine? Well, that's cosine. So this already is our u prime, and this is our u. So this would just simply be equal to the natural log of the absolute value of our argument, which is u, sine theta, plus c. Okay? All right, let me do something like this problem here. Go ahead and pause that video and see if you can work through this one. So here, the numerator doesn't appear to be the derivative of our denominator, but we can rewrite this, actually. We can rewrite this so that this would be equivalent to x minus 4 over x dx. That is to say, we're just dividing the numerator by our denominator. And so we can integrate each one of these terms individually. We can say that the integral of x is simply x squared over 2, right? The integral of x is just x squared over 2. Now, what is the integral of negative 4 over x? Pretty similar to what we did in number 1, our first problem here. This would simply be minus 4 times the natural log of the absolute value of x, all of that plus c. Okay? All right. I'll let you work through some of these other ones, and you can always check my solutions with what I have. Now, I also wanted to talk about, I want to get some of this out of the way. I also wanted to talk about some other methods for simplifying. Sometimes when we are working with integrals that involve the natural logarithm, we have to do a couple of creative strategies to rewrite it in a form that would make the integration a little bit more obvious. So there are a couple of different approaches here that I want to highlight. Let's start with the first one here. Let's start with division. So take a look at this integral here. We've got x cubed minus 6x minus 20 over x plus 5. Oftentimes, when we see that the degree of the numerator is greater than the degree of the denominator, what's often helpful is to go ahead and divide the numerator by the denominator, similar to what I did in my previous problem. So since my denominator is actually linear, I can actually do this synthetically pretty easily. We've got 1, 0, negative 6, negative 20. I'm dividing by x plus 5, so I'm going to place negative 5 out here. So I've got 1, negative 5, negative 5. This would then give me 25, 19, and 19 times 5. This is going to be negative 95. So this gives me negative 115. So x plus 5 is definitely not a factor of x cubed minus 6x minus 20. But what this does do is that it allows us to rewrite this integral as the following. This is equivalent to the integral of x squared, using what I got as my result from synthetic division, minus 5x plus my constant of 19 minus 115 over x plus 5 dx. Now that I've written it like this is actually a pretty easy integral to, or pretty easy function to integrate. We can just integrate each term, so just using the power rule. So this would be x cubed over 3 minus 5x squared over 2 plus 19x. And this one right over here, as we've seen before, we can move that 115, that negative 115 to the outside. So we're really just integrating 1 over x plus 5, which is then just negative 115, the natural log of our u, or our argument, x plus 5 plus c. Okay? All right. Let's try another approach. Take something, look at here. We're a classic example of U substitution. Well, here we see that the numerator is not just the denominator, not just the derivative of the denominator. So unfortunately, it's not just written as u prime over u. Or is it? If I thought of u as being my more complicated function, or natural log of x, and I said let u prime be its derivative, 1 over x, I should probably write this, dx, can we rewrite our integrand now so that it actually follows the structure of u prime over u? Well, yeah, we can. This, we would say, is equivalent to 1 over x times 1 over the natural log of x, where we could see this would be our u. And this is equivalent to writing this as 1 over x all over the natural log of x dx. This is the same thing. This is our u. This here is our u prime. Okay? So actually, we do have the structure u prime over u. So this would indeed be the natural log, where our argument now, what we're taking the absolute value of, is u, which is the natural log of x. Make that a little bit more obvious, plus c. All right? Okay, let's try another type of problem that's similar to U substitution, but we're going to have to change a variable here. So let me make sure I have enough space to work with this one. Okay. All right, so let's take a look at this one. Again, I'm going to set this up so that u is equal to x plus 1, in which case the derivative, or u prime, or du, I should say du, is going to be just dx. Now, it doesn't look like, no matter what we do, that du is simply just going to appear here. So we're going to actually have to rewrite x in terms of u. So we're going to say x is equal to u minus 1 if we isolate x. So if that is the case, we can rewrite this as follows. I'm going to take this 2 and I'm going to move it, since it's just a constant, I'm going to move it to the outside. I'm going to write this as 2 out here. X I can rewrite as u minus 1. The denominator is simply going to be u squared. And since dx is equal to du, I can just write this as du here. Okay? Now that I have that, I can go ahead and divide the numerator by the denominator. So this is going to be the following: u over u squared minus 1 over u squared du. And I can put this in parentheses if it's confusing for anyone, but that du kind of implies everything prior to that is simply our integrand, which then simplifies to 1 over u squared, or 1 over u, excuse me, minus 1 over u squared, all of this du. Okay? And if we go ahead and integrate each one of these terms now, we get the following. We'd say 2 times the integral of 1 over u is simply the natural log of the absolute value of u. Okay? 1 over u squared, that would be negative 1 over u. That integral would be negative 1 over u, but since there was already a negative there, that's going to be plus 1 over u. All of this plus c. So if we then substitute what 2 is equal to, we get 2 times the natural log of the absolute value of x plus 1 plus the natural log of, oh, excuse me, that's already been integrated. So that's just going to be 1 over x plus 1 plus c. All right? Okay. Let's try this last one here as another example of a kind of a change of variable problem. So here again, we're going to let u be equal to kind of a more complicated expression here, root 2x, because then we could see here that du is then equal to, well, there's a couple things. Actually, before I do that, something that might be more helpful. I mean, look, we could write du is equal to 1 over root 2x dx. So we could proceed as such, right? In which case we would say that root 2x du is equal to dx. That is possible. We could proceed as this. But since that doesn't appear to be super helpful for us within the context of this problem, there's something else I want to do here. At this step, since we're dealing with a radical, I want to actually square both sides and write this as u squared is equal to 2x, okay? In which case now the derivative, this would be 2u du is equal to 2 dx. which then allows us to say that u du, if I divide both sides by 2, is simply equal to dx. And I think given what we actually have written in this integrand, this is a lot more helpful. Why is that? So let me clear this out of the way. Although, again, you could have used this and probably arrived at the same step. But if I rewrite that as the following, 1 over 1 plus u, dx is equal to u du. Okay? Well, since I'm multiplying 1 over 1 plus u times u du, I'm going to rewrite this as u over 1 plus u, or u plus 1 du. Now, from here, we've got two different options of things that we can do. Okay, let me show you the first. So the first option, let me just highlight this as the first method, is I could go ahead and try to divide the numerator by the denominator. Okay, so if I divide the numerator by the denominator, I can kind of maybe even set this up long division wise if this helps at all. So u divided by u plus 1, well, this is going to be 1, u plus 1, subtract all that. We get negative 1s, meaning our remainder is 1 over u plus 1. So I could rewrite this integral as the following. U over 1 plus u is going to be equal to the integral of 1 minus 1 over u plus 1 du. Well, if I integrate each of these terms, this is going to give me the integral of 1 is simply u. The integral of 1 over u plus 1 is going to be the natural log of the absolute value of u plus 1 plus c. And then substitute in what we've defined for our u. So we've got root 2x. Make that a little neater. Root 2x, all of this is under the 2x, plus the natural log of, minus, I should say, minus the natural log of the absolute value of root 2x plus 1, all of that plus c. Okay, so that is our first option, just divide the numerator by the denominator. Let me do another approach here from this step, after this step here. So after this step, if we don't want to actually divide the numerator by the denominator, another approach is to do the following. Well, let me actually rewrite that here so we can see it. U over 1 plus u. And another approach actually is to go ahead and add 1 and subtract 1. This is something that we'll commonly do with later integrals. And hopefully you see why. By adding 1 and then subtracting 1, I'm able to rewrite it as such. This is the integral of u plus 1 minus 1 over u plus 1 du, which we can then write as two separate integrals. We can say this as u plus 1 over u plus 1 minus the integral of 1 over u plus 1 du. And then from here, this just simplifies to 1 minus the integral of 1 over u plus 1 du. Let me actually rewrite this so I can include that in derivative. And then from there, from this step, we have effectively the same thing that we did from here. You can just integrate each one of those terms individually. Okay, so hopefully this gives you a sense of a couple of different strategies that we use or employ for simplifying integrals that result in the natural log of u, or the natural log of some function x. And the tricky thing about this is it's not always going to be immediately obvious. And this is why just repetition and experience and practice working with these types of integrals are going to be so helpful. The last type of problem that I just want to quickly discuss before we close, and again, I already went ahead and wrote this out, so I'm going to delete that, not to spoil it for you all, is just looking at some integrals that do actually result in the natural log function from trig functions. And that's effectively just integrating tangent and cotangent. So up to this point, we didn't really have a way of integrating tangent and cotangent. But look at tangent here. We can actually rewrite this as the sine of x over the cosine of x dx. And ask yourself, is there a way that we can kind of use what we've learned so far about integrating functions that result in a natural log here? Well, we know that if we were to treat this function down here, cosine, as u, this is pretty close to being u prime. All that we are missing is if this were a negative sine x? If this were simply a negative sine x, then this would exactly be u prime over u. Well, that's easy. We can multiply this by -1 as long as we also multiply by -1 here. So we're not really changing the integrand. Now we see that it is indeed u prime over u. So we can then say that the integral of tangent x, which is equivalent to integrating sine x over cosine x, is simply negative natural log, absolute value of cosine x, all of that plus c. Okay? So in general, we can say that the integral of tangent of u times u prime is equal to the natural log of the absolute value of cosine u plus c. Absolute value of cosine u plus c. And pause the video right now and see if you can come up with a similar rule for cotangent. Well, this one's even easier. We know that the cotangent is cosine x over dx, or sine x dx, and the derivative of sine is indeed cosine. So this is already set up. So this already follows the integral of u prime over u. So we can say that this is the natural log of the absolute value of sine x, all of that plus c. So in general, we can say the integral of cotangent of u times u prime is equal to the natural log of the absolute value of sine u plus c. Okay? So one quick practice problem that we might do with something like this, if we were looking at something like number 12 here, the tangent squared x dx. Well, I know that tangent squared dx at first glance would just be tangent x times tangent x. That doesn't help us too much. But if I can use a Pythagorean identity to rewrite tangent squared x as secant squared x minus 1 dx, then I can split this up into two separate integrals, or I could just think of integrating each term. What is the integral of secant squared x? Well, that is simply tangent x. What is the integral of -1? That is negative x plus c. Okay? Might as well try one more with you all, just to wrap up the video. How would we integrate something like this? Well, it's actually surprisingly easy. This is u prime if this here is u. So this is simply the natural log of the absolute value of sine x minus 2 plus c. All right? Hopefully this helps give you a sense of how to integrate functions that result in the natural log function.